Hello and welcome back to Introduction to General Relativity. In this lecture we're going to study the geodesics of test masses and bodies in the Schwarzschild solution. Calculations in this and the following lecture will allow us to actually understand some of the most significant tests of the general theory of relativity. Now, the objective really today is to study, as I said, the motion of a particle in the Schwarzschild solution. We're not just going to study a general trajectory, however. We're going to study particles in motion around the outside of a heavenly body, because of course we can all get an idea of what the trajectory of a test mass that actually impacts the sun will be. There won't be any particle after it impacts the surface of the sun. So we're only going to worry about test masses that go around the exterior of a heavenly body, such as the sun. And so if we draw the sun here, right, blob of superheated gas, then we're interested in trajectories which orbit around, say, the sun or some star or something. And we're going to introduce some notation before we get into the full derivation of this trajectory. So our goal is this black line, to understand this black line. So if this black line here, this is the curve under question, we call it gamma maybe. So for a curve gamma, and we demand that this curve is parameterized by some parameter, let's call that parameter tau. We're going to introduce the notation UA is for the tangent vector to the curve. We're going to also use the Schwarzschild coordinate system. So in that case, it makes sense to actually express UA as in the coordinate basis. In which case, we use the Greek letter now to denote the index, because we're using a specific coordinate system. And these components are nothing other than the derivatives of the coordinates with respect to the parameter tau. Now we're only going to focus on time-like geodesics. We will focus in the next lecture on null geodesics. There's not really any point in focusing on space-like geodesics, unless you believe that there exist particles that move faster than the speed of light. So for time-like geodesics, tau, this parameter, we're going to choose it to be the proper time. That affords us some simplifications. In the case where we consider null geodesics, light rays, we can no longer choose tau to be the proper time. It doesn't make any sense. We're going to choose it to be the affine parameter, which is defined as follows. You just choose tau so that the covariant derivative of u along the tangent vector vanishes. Remember, there's an extra affine freedom in choosing these curve parameters, so that this equation is only satisfied for one particular choice. Now remember, we're in the plane, right? In the previous lecture, we discussed symmetries, or the previous lectures, symmetries of the Schwarzschild solution. And one of the key symmetries is rotational invariance. And without loss of generality, we can choose theta, the theta coordinate, just to be the pi over 2. So now we can investigate the length of our tangent vector to the curve. And this will turn out to be a very useful formula. So the length with respect to the metric of this tangent to the trajectory of this free particle moving in the Schwarzschild under the gravitation of this heavenly or celestial body admits the following formula in terms of components. And depending on whether or not you have a time-like or null geodesic, this is either 1 or 0, right? Because if it's time-like, we're using proper time, and we're normalizing this to 1. So this turns out to be quite a useful formula. So we'll box it up. Then we also know something more from the previous lecture. See, at this stage I should pause and say, what are we trying to do here? Well, we're trying to solve for these coefficients here. So what are we doing at the moment? Well, we aim to solve for the position of our test mass, right? Whatever, given some initial conditions. So we've got t, we aim to solve for t, r, and phi, and also theta, right? But that actually equals pi over 2 by the symmetries of the problem. And so what we're going to do is we're going to write down enough equations that can deliver us the derivatives, a complete set of ordinary differential equations for t, r, and phi. And we're going to be, you can just write out the geodesic equation, right? There's one strategy that you could do. It's a procedural strategy. You don't have to think. You write down the geodesic equation, and that's all fine and good. And you can do that. And in fact, in some textbooks, they really do write out the geodesic equation using the Christoffel symbols that you find for the Schwarzschild solution. However, there turns out to be a far more economical way to get to the complete set of differential equations for t, r, and phi. We could use geodesic equation. However, there is a much more economical way. And that's using, and this is the way that we use also, this is pretty much the strategy one exploits classically in the Newtonian world. And that is to use constants of the motion. So that's actually, if you write down enough constants of the motion, well, you've completely determined the trajectory. Now, because the Schwarzschild solution has so many symmetries, and we're going to be able to write down quite a few constants of the motion, more than one, and that turns out and will turn out to be enough to determine the trajectory. So thanks to this proposition in the previous lecture, right? Remember this proposition about killing vector fields and geodesics. So we proved that if you have a vector, a killing vector and a geodesic, then the inner product of the geodesic tangent vector and the killing vector is constant. It's a pretty important result because it gives us constants of the motion. The more killing vector fields you have, the more constants of the motion. So there it is, right? The inner product of psi a ua, which is just the metric, right, times psi a upper ub upper. So the more killing vector fields you have, the more constants of the motion you have. That's a pretty impressive and useful result, because some solutions to the Einstein's field equations, they have natural big isometry groups, and associated to an isometry group is a killing vector field, and associated to killing vector field are constants of the motion. So let's choose our first and favorite, always our killing vector field, the one that generates time translations. And corresponding to this vector field, we have the following constant of the motion, which has a name, right? What is it that doesn't change as time passes? Well, we give it a name in physics, that's called the energy, right? Although in general relativity, one must be very careful about what one calls the energy. Because you also have to incorporate the gravitational field itself. So actually the question of what's the energy of some of the volume of space-time, including test particles and so on, can be difficult to make precise. We'll continue to call this the energy, despite these subtleties, because in the special relativistic limit, this really is the energy. So if you try and solve for the motion in special relativity, then you get that this quantity E is the energy per unit mass. Of a particle measured by a static observer. But ultimately, whether or not it's the energy or not doesn't really matter for our goal today, which is to solve for the motion, solve for the trajectory or the geodesic followed by our free particle. So all you should really note is that equation I is got a constant on the left hand, and on the right hand side a derivative of t that'll allow us to that delivers us one ordinary differential equation. Actually we have two now, because remember we got equation star. Equation star is also a differential equation involving t, r and phi. So we have two differential equations now involving t, r and phi. Once we have a third, we'll have enough, and we'll be able to solve for the motion. So a little bit more on the interpretation of this E thing. In the null case, you can think of H bar E as representing, now we're invoking quantum mechanics a little, the total energy of the photon. Now this is a constant of the motion corresponding to the killing vector field of time translations. There's another killing vector field that we haven't spent yet. We spent one in just restricting our attention to the equatorial plane, right? We spent one symmetry that way. We have spent a second one, time translation, now to get this energy constant of motion. We have one other generator of symmetries, namely a second rotation, right? Rotation's about by phi. So you can look at the generator of a rotation in the phi coordinate. That gives you another Killing vector field, psi a. And corresponding to that, we also get a constant of motion. And we're going to call this constant of motion suggestively L, right, for various reasons, as we'll see. And you can interpret this one really as the angular momentum per unit rest mass of a particle on the trajectory, or as the quantum angular momentum of a photon. So you can think of this h bar L as the angular momentum of a photon. You don't have to. L is a constant, E is a constant, and this equation here has a constant right hand side. You can choose to interpret these constants, you don't have to. Interestingly, if you look at the right hand side of equation 2, you should recognize this from orbital mechanics in the Newtonian setting. So constancy of L in Newtonian physics is Kepler's second law, right? Which means that equal area is swept out in equal times. Okay, we've got three equations now. We've got equation star, which is a differential equation. We've got equation 1, which is a differential equation. We've got equation 2, which is a differential equation. And we could just try and brute force solve these nonlinear coupled differential equations, but actually we get lucky, and it's pretty easy to solve these equations. We can eliminate quite a few already. So just by simply substituting 1 and 2 into star, we get an equation, very useful equation, that will almost give us the solution already. And you'll see what I mean by almost in a second. And so this kappa is a constant equals +1 for time-like and 0 for null. Now, why do I say almost solved? Well, check it out, right? This equation has two bits to it. There's firstly, there's an half r dot squared. And secondly, I mean, well, a zeroth observation is like this equation involves only r. So it's an ordinary differential equation involving r. That's already pretty fantastic. We've reduced the whole problem to quadratures now. So what we've got is I'll suggestively label the two terms here, the first term as a kinetic energy type term, and the second term as a kind of potential energy like term, and the right hand side is kind of like an energy, total energy type term. And if you look at this equation, you know, with thinking about those words, then you should recognize this equation that we've in the red box here, the yellow box, You should really recognize this as a equation of motion for a particle, a free particle of unit mass, under the influence of this potential, a strange potential here, and with the total energy half e squared. Now, this is sort of one of the most familiar aspects of mechanics, right? We've got a kinetic, potential, total energy. We know how to work with such things. And we're going to import and exploit all the knowledge we have of one-dimensional mechanics to solve this equation. And so our strategy will be just as in classical orbital mechanics. We're going to solve for the radial motion first, and then we're going to use the other equations to determine the angular motion. Now, if you look at this potential VR here, this effective potential that we've written down, actually, it should be pretty familiar to you from orbital mechanics. Like in fact, it's comprised mostly of stuff that we already see coming in Newtonian level of physics, right? The first three terms, effectively, are what you would expect from orbital mechanics. Only the last term is new or presents a new additional term that's not present in the Newtonian physics setting. So the first three terms should be completely familiar from Newtonian physics. The extra term that's new is this minus ml squared over r cubed. And what does it do? Well, it doesn't do much when r is big, right? It's quite a small perturbation when r is large. In fact, it only plays a role when r is small. But when r is small, it does a massive effect, right? It dominates over the centrifugal barrier. And so you can already get a sense that we can expect some rather interesting behavior, right? As compared to the Newtonian setting. So now the goal is to solve all these equations. Well, we're going to solve for r first, right? And we can do that because it's really quadratures now. So if we take a look at this, the radial equation, right? You've got a first derivative of r. It's got the classical kinetic plus potential energy structure. We can just integrate this equation. And you get the following integral. And you have to take a square root along the way. That's why there's a plus or minus sign there. But otherwise, it should be a completely straightforward exercise to verify this calculation if I haven't made a mistake. And that's it. We've already worked out the angular motion now. Oh, I even skipped a step. Sorry about that. I've already jumped ahead. So I'm not solving for r at all. Just realized I've written down the angular motion. You can do this by eliminating the tau dependence from equations 2 and star. And that's how you arrive at this equation here. So what do I mean by that? So if you look at equation 2, 2 is super simple, right? It's just r squared phi dot squared. And star is this somewhat more complicated equation here. And the trick here is to express, I mean, I'm not going to do this full calculation. It's a couple of lines. I'll give you some hints, right? So equation 2 says that L equals r squared, and I'll actually write out the derivative so you can see what's happening. D tau squared. So you rearrange that. So that's L on r squared equals d phi squared d tau. Oops, d phi d tau squared. And now we want something like d phi dr that we can then integrate. That's the objective. So we don't have that, right? If you look at the equation 2, 2 gives us something with a proper time, and we need to eliminate the proper time. So one way to do that is you can just do it like this, right? You can just say that d phi dr equals, well, it equals d phi d tau times by d tau dr. Okay, and then that thing, we can get this from star, from equation star, right? D tau dr is just dr d tau inverted. And where do we find it? Well, we can go back to equation star, and there it is. It's buried in here, right? There it is there. So r dot squared. Or we can, yeah, that's one way to do it. Go ahead and do it that way if you like. And then you should end up, hopefully, with the equation that I've written down. So actually, I've just gone ahead, forget the radial motion, I just went ahead and solved for the actual full trajectory. Although you could certainly solve for the radial motion and then solve the other equations to get phi. Given that now, we can actually analyze and study these orbits. Well, actually, we can learn a lot just by thinking about this potential and kinetic energy interpretation. So the name of the game now is to actually consider these orbits, to understand these orbits, and now to look at their stability. And actually, we're going to start with stability questions. So to make life simple, for the rest of this lecture, we're just going to focus on the time-like geodesics now. The null geodesics we leave to the next lecture. And now, what is a stable orbit? Well, a stable orbit is one where the radius does not change with time, right? And if we look back here, when would that be? Well, that would be an extrema of the potential energy, right? And I'm going to draw some pictures to explain that in a second. And so what we're going to do is find the extrema of the potential energy. So if we look at our effective potential term, where are the extrema? Well, they're just, when you take the potential and differentiate it with respect to r and set it to 0, that's where the extrema are. So if you do that, take the potential and you do the derivative, then hopefully you should arrive at this formula. And we can just straight away cancel off the r to the 4. And we're left with a quadratic equation. So we can just write out those zeros. We've got two kinds. We've got r plus and we've got r minus. From the quadratic formula. And, well, when do we have two solutions and when do we have no solutions? Well, when the term in the square root here is negative, then we don't have any real solutions any longer. So in particular, if L squared is less than 12 times m squared, there are no extrema. So for small angular momentum, and what does the potential look like now? Well, in that kind of setting where L squared is less than 12m squared, then the potential has this kind of look. There are no extrema. Here I've plotted it for 6m squared. And so no extrema means that if you put a particle in that potential, remember the interpretation of the radial equation of motion is that of a unit mass particle moving in this potential, then no matter where you stick the particle, there is a gradient and it's going to sink down, right? It's going to zoom down into the center. So what would that mean in terms of an orbit? That would mean an orbit that spirals or just goes directly into the center of the celestial body. So in that case, there are no stable orbits. So there's not enough angular momentum, that particle's going in. Now, if you've got enough angular momentum, but in particular, you've got more than 12m squared angular momentum, then you can find the extrema according to that formula, right? Nothing's changed, the formula is still correct. But you could work out that one extrema is a minima and one is a maxima. You just got to do the second derivative to work out which one's a minima and which one's a maxima, or you just look at the plot. And what do you see? Well, in this sort of setting, what does the potential look like? Well, the potential looks a little different now. So we've got a maxima and a minima. Max, min, and here I've drawn it for, say, L squared equals 24m squared. And so you can see where the maxima and minima are on this particular curve. Right, here's a maxima and here's a minima. So this is R minus here. Oops. That's R minus there, and that's R plus there, the minima. So you can see that a fictitious particle in this potential would sort of roll around the minima here and fall down from the maxima. So in particular, it tells us there are stable orbits. And not only stable, they are completely circular, right? When the radius doesn't change, well, phi changes, that's a circular orbit. R dot is 0. There's also an unstable circular orbit, right? If you just get the particle, the test mass balanced in that potential there, then it will also execute a circular orbit, but of course the slightest perturbation will kick it out. And in the limit, right, we can get to the Newtonian non-relativistic limit to understand these points. R plus has the form L squared over m, which is the same as the Newtonian formula for the radius of a circular orbit. Now it's sort of important to note that r plus greater than, because r plus is greater than 6m, there are actually no stable orbits. Stable circular orbits. Okay, that's a fairly obvious consequence. Another one is that the circular orbits themselves, the unstable ones, in a bounded region, and they just lie between 3m and 6m. The energy constant now, so you can work out the energy of a particle in a circular orbit. Just substitute it into the equation above. It's a little substitution exercise. So what's the energy as a function of the radius of something in a stable circular orbit? Well, it's r minus 2m over the square root of r. Square root of r minus 3m. This will turn out to be kind of interesting in a second. So for small radii, like if r less than 4m, the energy is greater than 1. And so if we take a look, then we can see that if you have a particle perched at the top of this potential, I mean, it's kind of obvious from the picture, right? If you've got a particle in an unstable circular orbit, perched at the top of this potential, and you give it a little perturbation outwards, then you'll see that it escapes to infinity, right? It just flies off the potential. It has enough energy to carry it out to infinity. Of course, if you perturb the particle inwards, then it will plummet into the center. All right, now let's understand stable circular orbits, and in particular perturbations of stable circular orbits. This will lead us to one of the most celebrated predictions of Einstein's general theory of relativity. Well, confirmations rather than predictions, as you'll see. So let's suppose we have a particle in a stable circular orbit. What does that mean on our potential diagram? So our fictitious unit mass particle will be in that potential well now. So we've got this little particle here, and it's executing oscillations inside this potential well here. around the minima r plus. That's what it means to be in a stable, in a perturbation of a stable circular orbit. So if you look at that potential, then for sufficiently small distances away from r plus, the potential is going to look effectively quadratic, right? I mean, it's got some cubic corrections, but it's effectively a quadratic potential. So we can just exploit that observation to really quickly get a handle on the oscillations around this minima. So we're going to look at some sufficiently small displacements where the cubic corrections can be neglected, and then the particle will execute simple harmonic motion because it's a quadratic potential. And what's the frequency? Well, you just got to solve the harmonic oscillator. And that is a job for you. So the frequency of radial oscillations, we'll call omega squared r. You find that by just taking the second derivative of the potential around the minima. And it's just, well, when you work it out, it's just this ratio here of r pluses and m's. Now, I have to point out, of course, that the time here in this one-dimensional classical mechanics problem is the proper time, right? So this is as things are measured relative to the particle itself. But to the level of approximation, we will just set the two to be equal. So yeah, it's not the Schwarzschild coordinate time. T, right? Tau is different from T. So we've already worked out now that the particles execute these little oscillations around this stable radius. Now the particle is also, the test particle is also moving around the celestial body, right? Once every however many seconds. And we need to work out what is this angular frequency, right? How often does it go around the celestial body? Well, you can find it by just defining omega phi to be phi dot, right? Because whenever phi comes around 2 pi, well, then you've executed a complete oscillation. And that, right, is determined by the angular momentum and the radius. I've forgotten a square here, I believe. Actually, I'm just going to check that I got the angular momentum equation correct. I feel like there's an extra square that I wrote down that doesn't feel right. Indeed, I made a mistake earlier on. Sorry about this. Right, that looked awful strange. So equation 2 has a mistake in it from earlier. So do make sure to to pay attention to that. You would not have been able to do some of the equations, the exercises, so I'm sure some of you may have already in fact commented by the time we got this far. So okay, there was a mistake there. Apologize for that, sorry. So where were we? So there's definitely no squared there. Okay, so we're trying to solve for the angular motion of our test body. Well, by defining omega phi just to be phi dot, then we already can work out the period and therefore the frequency. Which is determined by the angular momentum. And the angular momentum we can eliminate with the equation above, which determines the zero of the circular orbit, the stable circular orbit, and then we work out that the angular frequency is this particular ratio here involving R plus. Okay, very good. So what, right? Well, the first thing I want to point out is that, and this is the sort of the most normal situation with this kind of setting, is that omega r is not necessarily the same as omega phi. Now, that's a bit different to the Newtonian setting. So in the Newtonian setting, things are like amazingly, beautifully symmetric and wonderful. There, omega r and omega phi are commensurate frequencies, just magically because of the nature of the potential, which is kind of amazing, right? But here, in this general relativistic setting, things are much less much more generic and much less miraculous. So, in particular, these two frequencies are incommensurate. But let's first talk about where they are almost commensurate. So for R plus is really large, so this is the Newtonian limit. What are these angular frequencies? Well, one of them is approximately m over r plus cubed, and the other one is approximately m over r plus cubed. Okay, so great. So in the far r limit, the larger r limit, these two frequencies are commensurate. They coincide. And the orbit closes, right? So this is what you expect from the old Newtonian stuff. You have a heavenly body, celestial body, here it is here. And you have a particle in motion around this celestial body. So what I'm going to do is I'm going to draw this trajectory here, say in orange. So let's suppose you have a stable circular orbit around the celestial body, and then you consider a perturbation around this celestial body. Then in the Newtonian limit, then this thing executes this simple harmonic motion around the minima, and the orbit closes. So that's the Newtonian limit. Great, fine. So everything matches up with what you know from the Newtonian limit. The impressive and amazing thing about general relativity is that in general, omega r does not equal omega phi, right? These orbits, these oscillations are incommensurate. And that means that the orbits do not close. And we get a procession of perihelia and aphelia. So perihelion and aphelion are the places where the orbit is closest and furthest from the celestial body. So redrawing the figure that we just had before. So the orange curve is the stable circular orbit. Consider a perturbation around the stable circular orbit. Now the particle oscillates as it goes around, radially oscillates, but these oscillations are incommensurate with the circular frequency, and so we get these characteristic unclosed orbits, which I'm not sure if I'll be able to draw. Right? And the point where the particle is furthest from the object, or closest from the object, changes from orbit to orbit. So the precession rate of the perihelion well, there is a precession. First of all, that's a kind of a key prediction here. And you can estimate this precession rate as being just the difference of these two frequencies, and substituting those numbers in, you arrive at the following formula for this precession rate. And for the not quite Newtonian limit, but for the limit where r plus is a lot bigger than m, this precession rate is approximately 3m to the 3 halves. R plus to the 5 halves. Now, this is a very, very small number, but for certain celestial bodies, it's non-trivial. It's a measurable number. And in particular for Mercury, this is about 43 seconds of arc per century. So if you observe the orbits of Mercury for 100 years, you'll start to notice that the perihelion Mercury are precessing around. And this was in fact known. And this calculation here constituted one of the most celebrated and stunning successes of Einstein's general theory of relativity, because it matched the actual observations of the precession of the perihelion of Mercury. In the next lecture, we'll be looking at another stunning prediction of Einstein's general theory of relativity, namely that light is the trajectory of light is curved or bent by the gravitational field, and that will bring us essentially to the end of this course. But for today, we're finished. Thank you very much, and goodbye.